In the first part, we want to write down a quadratic equation whose roots are plus or minus root k. Now there's a couple of ways we can look at this. One way is to go back to what we learnt in algebra, which is that the two roots of a quadratic equation are referred to as alpha and beta. So one root is the positive square root of k, and the other root beta is the negative square root of k. Then we know that we can form a quadratic equation with these two roots by writing down x squared minus x times the sum of the roots plus the product of the roots equals 0. So we can plug root k in for alpha and minus root k in for beta. So alpha is root k, beta is minus root k. And we have the product of the roots, that is root k multiplied by minus root k. Well, root k by root k is k. Root k by minus root k gives minus k. So we end up getting x squared minus k equals 0. You can see that root k minus root k is 0. We get 0 there. So this is our quadratic equation. There is no x term actually. We just have an x squared term and a constant term. The constant term is k, minus k. Of course, if you've forgotten this formula, you can see where it comes from. It comes from just taking the two factors. If root k plus root k is a root, then x minus root k is a factor of the quadratic equation. If minus root k is a root, then x minus root k or x plus root k is a factor of the quadratic equation. So these are the two factors of the quadratic equation. If we multiply them together and set it equal to 0, we get the quadratic equation. Multiplying this out, we will get x squared minus k equals 0, just like here. And it's very easy to see that this is indeed the correct quadratic equation, because if we move the minus k to the other side, we get x squared equals plus k, and if we get the square root of both sides, we get x equals the square root of k, and we have two values there. It probably should be emphasized that k must be a positive number. Well, positive number or equal to 0. Otherwise we can't get the square root. So it might need to be emphasized here that k is greater than or equal to 0. But anyway, that's not too important once you know how to get this out. In part 2, we're going to use the Newton-Raphson method to show that this rule, un plus 1 equals un squared plus k over 2 times un, can be used to find increasingly accurate approximations for root k. So we can refer to our function as f of x. So basically, we have a quadratic function, and it's a parabola. Quadratic functions have the shape of a parabola. It's an upright parabola because the x squared term is positive. And it will cross the x-axis at two values. And the values are minus root k and plus root k. So you see that the function is actually symmetrical about the f of x or y-axis in order that it has these roots. Now, in a previous video we covered the Newton-Raphson formula. The UNs are successive approximations to the actual root of f of x equals 0. If we put f of x, which is x squared minus k equal to 0, these UNs are successive approximations. Now, I actually used the letter xn in the previous video for UN, and xn was here, of course, and this would have been xn plus 1. But since the letter u is used, I'm going to use the letter u is used in this question, so I'm going to change xn to un and xn plus 1 to un plus 1. We already know what the roots are. We know that the root of this function is actually the square root of k. So we can use Newton-Raphson to get better and better approximation to the roots. So we would start off with an initial approximation, which would be called u1. u1 might be some value close to root k. Suppose we're looking for this root here. We'd pick u1 as some value close to this root. We would have the value of un. We'd plug it in here, work it all out, and we get out u2. And from u2 we can plug it into this right hand side to get out u3, and we can keep iterating and getting better and better approximations to the root. So the values of un should converge to root k. Now, f of un is just got by replacing x with un. So we get un squared minus k. In the denominator here we have the derivative of f at un. So we differentiate f with respect to x. That will give us 2x. The k is just a constant. We just get 0. So f prime of x is 2x, and we want to get f prime at un, so we plug un in here, so we get 2un in this denominator. Now we want to write all of this in this form here. So we could get a common denominator. Let's get a common denominator of 2un. That's the form that it's in here. We just have a single fraction with a common denominator of 2un. So we have un over 1 here. 1 into 2un goes 2un times 2un times un is 2un squared. And then we have minus un squared, and then we have minus k, that's plus k. So you see now we have 2un squared minus 1un squared, that's 1un squared plus k divided by 2un. That's the form that we want to get our formula in. In part 3 we want to use the above rule and take 3 over 2 as the first approximation for the square root of 3. We want to find the third approximation as a fraction. Okay, so you can see that the letter k has been replaced with 3. So our function becomes f of x equals x squared minus 3. And here's the graph of f of x equals x squared minus 3. So the roots are going to be root 3 and minus root 3. They're going to be the two roots of this quadratic if we put this equal to 0. Now the square root of 3 is about 1.73, and u1 is the first approximation. 3 over 2 is 1.5. So the first approximation would appear around here. It's less than root 3 actually. So this is u1. So we let n equal 1 in the Newton-Raphson formula, or this is the simplified Newton-Raphson formula. And if we let n equal 1, we get u1 plus 1, or u2, equals u1 squared plus k. K is now 3 actually, divided by 2 times u1. So we have the Newton-Raphson formula for a particular value of k. That value of k is 3. So we're solving this. We're trying to find the roots of x squared minus 3. So f of x is x squared minus 3. So u1 is 3 over 2, so we plug 3 over 2 in for u1. We have to square it here. We have to add 3, divide by 2 times 3 over 2. So what we get here is 9 over 4 plus 3. What's that? That's we get 21 over 4 divided by 3. That's like 21 over 4 multiplied by a third, or 7 over 4. So that's the second approximation. So this should be, in general, this is a better approximation than u1 is. Now let's get a third approximation. Third approximation basically means find u3. To find u3 we have to let n equal 2. So we get u of 2 plus 1, which is u3, which is what we want, equals u2 squared plus 3. We just plug 2 in for n. u2 squared plus 3 over 2 u2. So we just plug in 7 over 4 for u2. So we have 7 over 4 squared plus 3 divided by 2 times u2 divided by 2 times 7 over 4. So I've written the denominator as a fraction. It's 97 over 16. The numerator is 7 over 2. So we've 97 over 16 divided by 7 over 2. That's 97 over 16 multiplied by 2 over 7. So that's 97 over 8 sevens are 56. So this is U3. This is a third approximation to the square root of 3. If you want to see this as a decimal, I've written it out to 5 decimal places here. Here's the correct value of root 3 to 5 decimal places. So you can see that the first 3 decimal places appear in the third approximation. So the third approximation U3 is correct to 3 decimal places.